All right, let's get into it. Today, we're going to go on a little build-a-bot journey. We're actually going to construct a digital brain, basically from scratch. And by the end of this, you'll see exactly how a machine learns to read.
Now take a look at this. You and I, we know what this number is pretty much instantly. Our brains are just incredible at recognizing patterns, right? It doesn't matter if it's sloppy handwriting, weird angles, we just get it. But that leads to the big question, doesn't it? How in the world do you teach a computer, a machine that only thinks in numbers, to look at this squiggly line of pixels and see it the same way we do? Well, that's our challenge. So our mission, should we choose to accept it, is to build a neural network, a digital brain, one that can look at an image of a handwritten number and tell us with real confidence if it's a 0, a 1, a 2, all the way up to 9. Okay, first things first. Every student needs their study materials, so let's start by putting together the toolkit our little bot is going to need to go from a blank slate to a total expert in reading digits.
The foundation of its entire education is going to be this: the MNIST dataset. You can think of it as the ultimate textbook for learning numbers. It's this huge, famous collection of thousands and thousands of handwritten digits, made for exactly this kind of thing.
And when I say massive, I am not kidding. Our bot is going to study from 60,000 different training images. That means it's going to see a crazy variety of 7s and 4s and 9s, learning all the little subtle patterns of each one.
So you might be wondering, how does a bot actually see an image? It doesn't see a picture like we do. It sees a grid of 28 by 28 pixels. And to make it even easier for the machine, we basically unroll that grid into one long line of 784 numbers. Each number just represents how dark a pixel is. And that is what our bot is actually going to read.
All right, we have the textbook. Now we need to design the brain itself. Let's get to the blueprint and see how we're going to wire this thing up. Our network is going to have 4 main parts. It starts with the input layer. Think of these as the bot's eyes. Then the information flows through 2 hidden layers. This is where all the real thinking happens, or it starts to spot patterns like lines and curves. And then finally, it all comes together at the output layer, where the bot makes its final call. So let's just focus on the bookends here. The input layer's job, super simple. It just takes in that long list of 784 pixel values. The output layer's job is to give us the final answer. It has 10 possible outputs, 1 for each digit from 0 to 9.
So we have a structure, a kind of skeleton. But how does it actually think? Well, for that, we need some rules, some secret ingredients that let the information flow through the network in a smart way.
I mean, think about it for a second. As all this data is zipping through the layers, how does the brain figure out which signals are important and which ones are just, noise? It can't possibly treat everything the same.
The answer is this really clever tool called an activation function. In those middle hidden layers, we're going to use one called ReLU. And you can just think of it like a simple on or off switch for every little connection point or neuron in the brain.
And the logic behind it is beautiful in its simplicity. If a signal coming into a neuron isn't helpful, if it's a negative number, just ignore it. Turn it off. But if the signal is positive, it's considered useful, so pass it along to the next layer. It's a way for the network to focus only on what matters.
Okay, now what about the final layer? We don't just want some random internal score. We want an answer we can actually understand. And that's where another function, called softmax, comes in. It takes all the messy final scores from the brain and just tidies them up into a clean set of probabilities. So the bot might internally decide that the score for a 7 is 2.1, while the score for a 1 is negative 1.2. I mean, what do you do with that? Well, softmax transforms those raw scores into something that makes perfect sense to us. A 79% chance it's a 7, a 17% chance it's something else, and so on. And it all adds up to 100%. Perfect. Okay, so the bot can make a guess. That's a huge step. But how does it get better? How does it actually learn from its mistakes and improve for the next time? This all happens through a learning loop that has 2 key players. First, there's the loss function. You can think of this as the teacher. It grades the bot's answer and tells it just how wrong it was. Then there's the optimizer. This is like the bot's study method. It takes the teacher's feedback and actually adjusts the brain's wiring to do better next time. Now, here's the genius of our teacher, the loss function. It doesn't just say, nope, you're wrong.
If the bot was really confident about the wrong answer, the punishment, the loss, is way, way higher. This forces it to really learn from its biggest mistakes. And the study method, our atom optimizer, is just as smart. It follows a simple rule. If it's on the right track and making good progress, it takes bigger steps to learn faster. But if it's getting confused or uncertain, it slows way down and makes smaller, more careful adjustments. It's incredibly efficient. So we have the blueprint, we have the textbook, and we have the rules for learning. You know what that means? It's time for the training montage. Let's put all these pieces together and bring our bot to life. So in practice, here's what happens. We load up all 60,000 images, we get them ready for the bot, we build the model exactly how we designed it, input, 2 hidden layers, and an output. Then we compile it, telling it which teacher and which study method to use. And then we hit train and let it get to work. And after thousands and thousands of examples, countless tiny adjustments, and a whole lot of number crunching, it is finally graduation day. The training is done. So the big question is, did it work? Did our bot actually learn how to read? Yes, and it didn't just learn, it totally nailed it. An accuracy of 97.5%. That means that out of thousands of new, completely unseen handwritten digits, our simple little digital brain got it right over 97% of the time. That is awesome. So, we built a bot that can read numbers. Pretty cool. But why does a simple project like this really matter? Well, it matters because these exact same ideas, layers, activation functions, loss, optimization, these are the absolute fundamental building blocks behind the most advanced AI in the entire world. This little bot, this is step one on a really, really exciting journey.